basically, just sort of the general concept of what a black hole is, you might be wondering, well, how much would you have to actually compress the Earth in order to turn it into a black hole? And the answer is you'd have to compress it an awful lot. If you, with your magic wand, if you wanted to turn the Earth into a black hole, you'd have to compress it to a diameter of 1 inch. At which point, the Earth would become a black hole, and once you compress the Earth down to a diameter of 1 inch, it will just keep collapsing down to a single point at that point, because its own gravitational pull on itself will be so strong that there's nothing that can prevent it at that point from collapsing just down to a single point and turning into a black hole. Now, the physical theory that describes how black holes actually work and how space and time behave under such extreme conditions is Einstein's general theory of relativity. And if we use this theory, it's possible to solve for the full mathematical structure of a black hole. And here's just sort of a basic picture of what a black hole would look like. The point at the very center is called the singularity, and all of the mass of the black hole is squeezed down to this single point at the center. This is where essentially the laws of physics as we know them really sort of break down, and we don't know exactly what happens at the singularity, except that it is a single point of such unimaginable density that it causes a tremendous warping of space at that particular point. And all of the mass in the black hole is really just condensed down to that point. Now, surrounding the singularity, you have this boundary called the event horizon, and that is essentially the boundary of no return. Any object that falls through the event horizon will inevitably fall very quickly into the singularity and just be crushed to that single point at the center. So that would be a pretty unpleasant way to go if you ever happen to fall into a black hole. And then surrounding that, there's this other region that's called the ergosphere. And the theory of general relativity tells us that any rotating object will actually drag space itself into rotation around the rotating object. And a black hole, if it's rotating, can actually drag space into rotating very, very rapidly around the black hole. Space itself can rotate around a black hole. And the ergosphere is the region around the black hole where, if the black hole is rotating, space itself is dragged into rotation so quickly around the black hole that no object can remain stationary in the ergosphere. Any object that you put in that region will just be dragged into rotation around the black hole and eventually fall into the black hole. Now, we can't just turn objects like the Earth into black holes the way I showed you in that cartoon, but nature actually knows how to make black holes, and nature can create black holes. And the way that nature does this is by using extremely massive stars. Some stars are born much, much bigger than our sun. And for stars that are born with initial masses that are in the range of, we think, about 25 to 30 times more massive than the sun, or even bigger, those stars fuse their hydrogen in their cores into helium very rapidly. They fuse the helium into carbon and oxygen and heavier elements. And finally, they fuse these heavier elements in the core into iron very quickly, all in the space of a few million years, because these stars have tremendous luminosities and they're burning their fuel very, very rapidly. And finally, once the core of this giant star is made of iron, there's no further source of energy that the star can tap into. And at that point, the core of the star can collapse catastrophically. And for the most massive stars that we think exist in the universe, we think that the core will collapse catastrophically into a black hole and create a black hole.